Hello and welcome to yet another video of Cornerstones of Math. Today we are gonna play with these fractions, which are basically reciprocals of natural numbers. Now consider the sum of these three fractions, 1/2 plus 1/3 plus 1/4. The sum of these three fractions is greater than 1. Now, consider deleting the leftmost fraction, in this case 1/2. Then the sum of remaining two fractions, in this case 1/3 plus 1/4, becomes less than 1. But if we take that number and add three more fractions, 1/5, 1/6, and 1/7, then the sum becomes greater than 1 again. And you can already see where this is going. If we delete the leftmost fraction again, this time deleting 1/3, then the sum of remaining four fractions becomes less than 1. But just like we did previously, if we add next three fractions into the remaining part of the sum, then the sum becomes greater than 1 again. And we want to prove the generalized version of this right part. Can you prove that for all natural numbers n? So the first term must be 1 over n plus 1, so it gives 1/2 when n equals 1. Then we add up fractions 1 over n plus 2, 1 over n plus 3, and so on. Until what? Well, if we take a look at last terms, we have 4, then 7, then 10, then the number keeps increasing by 3 because we add 3 more fractions each time. So it is not difficult to find that the generalized expression of the last term is 1 over 3n plus 1. And we want to prove that this sum is greater than 1 for all natural numbers n. Alright, it actually took a whole lot of time to establish and explain the main problem, so let us not delay any further and jump right onto the proof. Here we use proof by induction, which is one of the most famous methods to use when we want to prove that the statement is true for all natural numbers n. But before we use the induction, let us first denote this expression for the left-hand side as an, so it is sort of an nth term of the sequence. Although it is not necessary for this problem, if you want to use the sigma notation for the shorter expression for an, you can say that the an is the summation of 1 over n plus j, where this j changes from 1 to 2n plus 1, right? So that the last term becomes 1 over 3n plus 1. Alright, now let's actually do the mathematical induction. First, the base case. When n equals 1, a1 is given like this, which we have already seen, and it can be easily shown that this is greater than 1. So the statement definitely holds when n equals 1. Second, the induction step. Suppose that for a particular natural number k, ak is greater than 1. So this inequality holds. This is the induction hypothesis. Then what we want next is to prove that ak plus 1 is greater than 1. Here you can simply substitute n equals k plus 1 in the general expression for an to find ak plus 1. But instead of doing that, let us think about how ak plus 1 can be constructed using the previous term ak. First, we delete the leftmost fraction, the very first term. So ak plus 1 starts from 1 over k plus 2. Then we keep adding up, and ak ends at 1 over 3k plus 1. Here, we have to add 3 more fractions to obtain ak plus 1, so we have to add 1 over 3k plus 2, 1 over 3k plus 3, and 1 over 3k plus 4. So this is the expression for ak plus 1. If we use ak, we can write it as, first, we subtract the very first term 1 over k plus 1 from ak. Then we add 3 fractions, 1 over 3k plus 2, 1 over 3k plus 3, and 1 over 3k plus 4. And let's write it as ak plus 1 equals ak plus these 3 fractions, 3k plus 2, 3k plus 3, 3k plus 4, and minus 1 over k plus 1. Here, obviously, we have to handle this part, and we want to handle it smartly. Doing so requires some intuition and ingenuity on handling inequalities, and there can be more than one way to go from here. I will go like this. First, I pick these two, 1 over 3k plus 3 and 1 over k plus 1. Here, the latter can be written as 3 over 3k plus 3, so we can easily carry out the subtraction and obtain minus 2 over 3k plus 3. Next, we handle these two, 1 over 3k plus 2 and 1 over 3k plus 4. If we add them up, we have this common denominator, and the numerator is 3k plus 4 plus 3k plus 2, so we have 6k plus 6 at the numerator, which I will write as 2 times 3k plus 3. Now why do I write the numerator in this way? Well, because if you expand the denominator, then we have 9k squared plus 18k plus 8. And what if we compare this with a fraction with denominator 9k squared plus 18k plus 9? Well, since this one has the smaller denominator, it must be greater than the other one. And why specifically 9 at the denominator here? Because this denominator right here is 3k plus 3 squared. So we have simply 2 over 3k plus 3. Therefore, we have this 1 over 3k plus 2 plus 1 over 3k plus 4 greater than 2 over 3k plus 3. So we have this. And previously, we have already obtained this. So back to here, relation between ak plus 1 and ak, we have ak, and this plus this is greater than 2 over 3k plus 3, so greater than plus 2 over 3k plus 3. And this minus this gives this, so minus 2 over 3k plus 3. So these two terms cancel out, and we simply have ak, which is greater than 1. The last inequality comes from the induction hypothesis. Now, you don't have to get frustrated if you couldn't come up with this entire process. You simply get better at this kind of things when you have more experience. Anyway, we have proof that if the statement holds for n equals k, then the statement also holds for n equals k plus 1. Therefore, we have our conclusion that for all natural numbers n, an, which is defined like this, is greater than 1. And that was all for today's video. Thank you all for watching, and if you enjoyed this video, please hit that like and subscribe buttons and explore my other videos in this channel. And as always, I will see you in another video.